So this is the first chapter. It's a kind of background information which gives some mathematical explanations or samples towards an understanding of the spectrality or the scale of space and why it's about harmonics which are constitutive for architectural space and how to control that. You know, with coding we talk about circular writing, and it's all about these circles and lines. We had it here with our constitution, and drawings are just with lines, and this is too flat to work on to get the richness of to articulate the richness of what we are able to put into proportion. So therefore, this interplay of the circles and lines, we want to focus on that in this short introduction and go a little in detail. So I think it's everywhere, and it's very common that this is a monochord, and here you see points in space as an instrument in a proportion. Like the Pythagorean proportion and harmonics, and then you see these kind of circles with different radius and their harmonic interplay, partitioning, and so on. So this is key to architecture. It always has been, and I want to give you an example how it works today in code in one-dimensional. So it's the most simplest way. So what we have here, so this is called in mathematics, it's the time domain. This is what we call in our primer the day or the space, which is a little confusing because it's called time domain, but we call it space. So let's go and say this is a certain unit, and you want to temper it. And now we're doing it with a frequency of 3. And then we have this wave, 3 waves. So, and they cut this space into 6 pieces. So this is an illustration of that. So what we have here with the blue line is the frequency. So this is what you can hear. So, and this is how the production of this space by circles is done. So this is a production. These are the circular line in time. So this is what you can hear. The red points, and so they are linear circles of space. And these are the actual articulations. This is what you can see. So this is irrational, this is rational points. So this is of reality, and this is of rationality. So therefore in space things are always discrete, and they are continuous, circular in time. This is reality. So this is a distinction. What we can do in mathematics, we can put that, we have it here now in discrete. Now, for example, these are 200 numbers along this axis. The same formula, it's sinus 2x frequency pi. We have the same here. We put it into 200 parts, and then we plot it, and we have the same line of time. So this is the reality of this line. So what we can do now is, it's called Fourier transformation. We look for this, take these data points, we make Fourier, and then we go for the, we kind of scan the frequencies or the production. So it's a kind of re-engineering of the production of these points here. So, and we see that there is at the frequency of 3, there's a high amplitude. So this mainly is a rotation of 3, of 1/3 of of this unit. So this is here. There are some small values because we don't have an infinite amount of points on this line. So, and now we can go with the frequency, so we can scan that reality, we can number it, and with these numbers we can go to production and render it again into these points. So this is the control of the production of this line, and we can scan the result and make a kind of re-engineering of the control parameters for the production. So this is what you can, in this case, therefore we had these numbers, you can see that points, so it's not a line, you can see. These are points in space, and this is a number of control over time. So important to see is that here, for example, we have data. We put it not now in the scene, but we make a line in space of points, just a single line, and we do the same thing with Fourier. And here we see we have different amplitudes for. So it's a horde of different frequencies in different amplitudes. So we can, for example, here look, that's df, this is the Fourier of that, and this is just the plot. So now we take the first 3 of these axes, 1, 2, 3 of these amplitudes of the first frequencies. So, and put that into our function. So it's 2x frequency, which comes from here via a pure function pi. If you put that, then we have a list of amplitude 1.2 sinus with frequency 1, 2 pi x, 0.6 frequency 2 pi x, frequency 0.4, frequency 3 pi x. So we can do it with 6, or we can go for 12. So then we see it's all the same mechanism. So now if to look at, so we go for frequency 3, then we get 3 sinus waves. So this is the frequency 1 with amplitude 1.2, frequency 2 with amplitude 0.6, frequency 3 with the amplitude 0.4. So this is a chord of 3 tones. If we add these chords, so go here for 3, so instead of plot mapping this, we make a total. So we add the amplitudes. So now we add the form. So, and then we see what happens. It's going towards our line. So this is a production of 3 tools towards this form. And we can increase the resolution by adding more frequencies. Or more frequencies. So, therefore, whatever form we have, we are able to produce it with the control with the control, and we can produce it in time with numbers controlling rotations in different strength, and we can go for any form. So therefore, form is result of a production and a chord of tones in certain proportions. So that's important to see. So we can do that in 2D. Same thing. Now we have a frequency of 3. Our formula now is, in this case, sinus with frequency 2 pi x, cosinus frequency x, 2 pi y. Go from O to 1, and render that. Then you see down, up, down, up, down, up, down, up. We start with 0 here with a sinus, with 1 here with cosinus. So that's 2D. This is interesting to see here. Instead of the density plot, we can make a map, a 3D curved plane. Then we are here, or we can cut it at a certain point. For example, if we cut it at sinus is equals 0, and then we want to have a contour where it cuts the horizontal plane around 0, and then we see at this grid. If we go to 0.5, then it's cutting just the top of the hill. If we go minus, it fills the valleys. So if we leave that, then we have these nice contour plots. And we have very architectural patterns. So now if we have this overlay of different frequencies, so this is simply one frequency, F3. Now again, we can make overlays to make a chord of frequencies in X and Y to produce any kind of image. So here we had any kind of form. Now we can have any kind of image. And to illustrate that, we can start here. So we have an image in time domain. So, Gerd Richter. We go for the Fourier, make color separate of this picture, image data to get just the image data of this color, so to get the gray and to have just the numbers, not the rendering of the image. Go for Fourier, and then we have the amplitudes and the phase. So the eye is always a phase, so which means if you put these frequencies a little off here, and this is off by 90 degrees. If you want to have it off by 63 degrees, you do it with the phase. This is the imaginary part, so you can move it. And you have the amplitude for each frequency. So that's it. So instead of looking at these patterns here, the chord of the different tones, we can have the same in 2D with something like this. Go for the image and render the frequencies in X and in Y. Then we are here. So, and now we can, for example, do the first 3 frequencies. So these are these frequencies and cut off. So make a high pass filter on that and render the picture. Go Fourier again, back. Go from this is the control of the production of this image, and then run the production and put it to reality. this is here, and we see what happens. This is our picture with a high pass filter of 3. Then we have RGB of the these are the color separated pictures, black and white pictures. If we go, for example, now to 12, then we get a better resolution. Or we can go to 24, and you see that with the control of very few numbers, we are able to produce a picture. So, and this sounds. So this is a horde of frequencies in a certain harmony. So that's, I think it's important that you only can see the rendering of a horde, and that you control this by numbers going towards the production of things. So this is what I think it's a temper of space. So do it with 3D. Then you get these fancy objects. This code is not, you can't do it on the cloud. So copy it, go to desktop. If you have a license, copy this code, and you see it takes a little time. Sophisticated. But again, it's a contour plot as we had it before in 2D. We say cosine by sin x plus cosine y by zx plus cos z by sin x equals 0. So, and then we look for this contour where this formula is equals 0 in space. And here we are with a nice object in 3D as a harmonic picture of tempering space. So it's a temperament of space. Good. Now we can go to architecture, and we look at this. So the hypothesis is that in architecture it's exactly like this. So what we see in space is, so we have to distinguish all these repetitions. So there are repetitions all over. So, and I think the architectural model is about these points in space. These are the harmonics. So these red lines I put there, or these points here. This is the architectonics. This is the harmonic of space. So this is the linear circle of space. So this is how to articulate space, which is here. Bam, 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 here. These are the rhythm of the whole thing. So whereas the filling here is a production. This is a product. So this is produced and done and realized with design. So these points in space. They are proportional and they are architectonic, whereas the product here corresponding to these curves, they are circular lines in time, and they are in the production hall. And this is design, strict contrast. And we have here, for example, in Blender, we have the object model. This is constituting elements in time, in space, whereas the edit mode is the configuration or the construction or the production of meshes in time. So these are a kind of the, like here, these are the traces of production, controlled by numbers and orchestrated like this. towards this outcome. And this clear distinction we want to follow, and by that our code gets simple and is able, in almost always the same way, is able to address whatever architecture we can imagine. Thanks for watching, and see you in the next chapter, where we focus on the doing of things. Bye.